Previously, we covered two mechanisms to establish trust in another party's public key and have shown how public key validation works within these two mechanisms. In this lecture, we will focus on hierarchical PKIs and see how more complex functionalities and services are handled and what impact the quantum computer will have. Since a certificate authority is central in a PKI, it has a lot of tasks and can quickly get overloaded. In practice, the CA therefore often delegates a lot of its tasks to other authorities, so that it can minimize its uptime and focus on the most critical tasks. Since it is a trust anchor, it is a very interesting target for adversaries. Another advantage of delegating tasks to other authorities is that the CA can reduce its attack vector, exactly because it has less uptime. Common authorities in the PKI with delegated tasks are the Intermediate Certificate Authority, the Registration Authority, RA, the Validation Authority, VA, and the Policy Authority. We will now go further into the different services in a PKI. The first service we will talk about is certificate revocation. For example, it is possible that Alice accidentally loses their private key, or sends their private key to someone else, or that someone breaks into their computer and steals it. In that case, there needs to be a way to communicate to other users of the PKI that this public key should not be used anymore. One mechanism that partly solves this problem is setting expiration dates for certificates. Each certificate documents until when it can be used. If a private key is compromised, then the corresponding public key will only be used until the expiration date, which reduces the period in which the compromise can be used for malicious purposes. When a certificate expires, the owner can request a new certificate that will be valid for a certain amount of time. There is also a way to actively track revocation events. Within a PKI, validation authorities are in charge of tracking the status of certificates and updating them if a compromise happens. If I want to check if I can trust Alice's public key, I will check the certificate and verify the signature. If it is indeed a valid signature from the CA it was issued by, I need to consult the VA. The VA manages two lists of certificates that were issued within the PKI and were revoked before they expired. The first list contains certificates issued to end users, so not other CAs, called the Certificate Revocation List. The second list contains certificates issued to the certificate authorities, called the Authority Revocation List. It is not necessary to keep track of expired certificates, since a verifier would already reject its validity based on the expiration date on the certificate. Additionally, if a revoked certificate expires, it can be taken off of the CRL or ARL, since a verifier would already reject it. There are various ways that a VA can communicate the status of a certificate to a verifier. Originally, if I wanted to check Alice's certificate, I would request the entire CRL from the VA and check whether the certificate is on there. As the CRL can grow quite large, this requires a lot of bandwidth and is not very scalable. An alternative is to use the Online Certificate Status Protocol, or OCSP for short. I can use this protocol to ask the VA to check for me whether Alice's certificate is on the CRL. The VA then sends me either a good, revoked, or unknown. Good only means that the certificate is not on the list and does not convey any information about whether it has expired. Revoked means that the certificate is on the CRL and has been revoked. Unknown is used if the issuer of the certificate is not known to the VA. The downside of OCSP is that the VA needs to be online and respond in time, which can be challenging for operational situations that require fast certificate verification, like the internet. An alternative for these cases is for a certificate holder to request a very short-lived certificate at short time intervals. For example, Alice could request a certificate with a validity period of 10 minutes. After 10 minutes, she will request a new certificate for 10 minutes, and so on and so forth. When I receive this certificate from Alice, I can accept the possibility that the certificate has been revoked within those 10 minutes and therefore not contact the VA for the latest status. An intermediate CA is an authority that can issue certificates on behalf of the main CA. In a PKI with more than one CA, the main CA is called the root CA. The root CA is a trust anchor of a PKI. The root CA issues a certificate to a set of intermediate CAs in the PKI, which we will call level 1 intermediate CAs. If I want to validate Alice's certificate that was issued by a level 1 intermediate CA, I can backtrack the origin of the intermediate CA. I will check in the certificate of the intermediate CA that issued Alice's certificate to see which authority issued the certificate of this intermediate CA. If this is the root CA of my PKI, then I can trust the certificate. Intermediate CAs can also issue certificates to other intermediate CAs. If a level 1 intermediate CA issues a certificate to another intermediate CA, we call the second CA a level 2 intermediate CA. This way, a hierarchy of CAs is established. In order to validate a certificate of any intermediate CA, we can recursively apply the process that we explained for level 1 intermediate CAs until we find the root CA. In practice, a certificate contains signatures and accompanying certificates for all the CA that are required to establish a path to the root CA. That way, when I want to establish the veracity of Alice's key, I can check if the signature of the CA that signed Alice's public key is valid, which in this case is a signature made by CA 2.4. To determine whether the public key that was used to sign the certificate belongs to that CA, I will check the certificate of CA 2.4, which was signed by CA 1.2. I will then check the signature and verify that the public key indeed belongs to CA 1.2 by checking its certificate. Since the certificate for CA 1.2 was created by the root CA, I can verify the signature and determine that I can trust the relation between Alice and public key 0x2222. The registration authority is in charge of validating a user's credentials. If these credentials have been deemed valid, the RA will request a root CA or an intermediate CA to issue a certificate for the public key of the user. Alternatively, if the user does not have a public-private key pair yet, they can request a CA to generate a key pair for the user and issue a certificate for that public key. The policy authority, or PA for short, is an authority that is responsible for creating and publishing all policy-related information. The two main documents a policy authority needs to create and disseminate are the certificate policy and the certificate practice statement. The certificate policy lays out the requirements to which each CA should adhere. The certificate practice statement of a CA describes how that CA fulfills its requirements from the certificate policy. The certificate practice statement is usually written in a standardized format. An example is RFC 3647 by the IETF. Such a certificate practice statement also includes how security audits are performed. Security audits focus on various aspects of a PKI. For example, they determine whether the certificate practice statements and certificate policy are consistent, and they also inspect the logs of the CA to determine whether the processes are executed according to the stated policies. Up till now, we've only talked about certification in one direction. The root CA issues certificates for level 1 intermediate CAs, and they in turn issue certificates for level 2 CAs, etc. However, it is also possible for PKIs to be linked through a method called cross-certification. In this case, we pick one CA from each PKI and let them sign each other's certificates. This way, any certificate that was issued by the cross-certified CA from the first PKI can be validated by anyone who trusts the cross-certified CA from the second PKI. These two CAs are also referred to as bridge CAs. In other words, bridge CAs enable compatibility between PKIs. From PKI 1's point of view, the bridge CA of PKI 2 is an intermediate CA within PKI 1. It is also possible to appoint a specific CA that is not part of either PKI to act as the bridge CA. All in all, it is clear that digital signatures are paramount to the workings of a PKI. The migration to quantum-safe cryptography means that new encryption algorithms will be used. The migration will introduce new algorithms for encryption as well as digital signatures. If a PKI is used to validate the public keys of these post-quantum encryption schemes, then the signatures used in the certificates will also need to be post-quantum secure. The main complexity with regards to migration of PKIs is the fact that not all users and authorities will be able to migrate at the same time, so mechanisms and policies will need to be put in place to streamline this migration. Important questions are: until when will the PKI support classical cryptography? Will post-quantum signatures be deployed in parallel with the classical cryptography? How will we combine classical and post-quantum signatures? To sum up, hierarchical PKIs can be very simple, with only one central authority, or very complex with multiple authorities with delegated roles. Digital signatures are paramount to the workings of a PKI. The migration to post-quantum cryptography will require clear policies and dedicated cryptographic solutions for these policies. See you next time.